Welcome to this explainer. I'm so glad you're here today because we're going to unpack a truly fascinating journey. We're diving into the exact science, the engineering, and the real-world application of transforming everyday plastic waste into high-value energy. It's literally a journey from trash to treasure, and the mechanics behind it are pretty mind-blowing. What if the plastic wrapper from your lunch could actually fuel your car? Seriously, think about that for a second. We're so conditioned to see plastic packaging as this terminal problem, right? As something that just inevitably ends up in a landfill or floating in a river. But what if we challenged ourselves to rethink that everyday waste as a potent, completely untapped energy source? That is exactly what researchers and engineers are doing right now, and the results are incredibly promising. Here is our roadmap for today's explainer. 1. Turning plastic into oil. 2. Inside the pyrolysis machine. 3. Finding the perfect temperature. 4. Testing the pyrolysis oil. And finally, 5. Scrubbing the toxic exhaust. Let's jump into section 1, turning plastic into oil. The magic word here is pyrolysis. It's a thermal decomposition process conducted entirely in the absence of oxygen. So the crucial point to remember is that we aren't just tossing plastic into a bonfire. If you burn plastic with oxygen, you just get toxic smoke and ash. Pyrolysis is completely different. We're essentially baking the plastic in an oxygen-free chamber. By applying intense heat without that oxygen, the long, complex polymer molecules of the plastic are forced to break apart safely into smaller hydrocarbon chains. That yields oil, some gas, and just a bit of solid residue. Moving right along to section 2, inside the pyrolysis machine. To understand how this works in the real world, we can look at a mini-scale prototype developed by researchers. It utilizes a batch reactor constructed from 3 to 5 millimeter thick carbon steel. Now, why carbon steel? Well, because this tank isn't just getting a little warm. It has to survive massive thermal loads and intense internal pressure as the solid plastic expands into hot vapor. It's basically built like a tank to keep the oxygen out and the high-pressure hydrocarbon vapor in. The flow of a system like this is, honestly, so clever. Step 1 is the heat source. Instead of using expensive, fresh fuel to heat the machine, this prototype uses an eco-friendly used oil burner, literally taking waste oil to process waste plastic. Step 2, the plastic inside the batch reactor vaporizes into a dense hydrocarbon gas. Then, step 3, that hot gas travels into a galvanized steel spiral condenser that is completely submerged in cold water. That sudden drop in temperature forces the hot gas to condense into a thick, energy-rich liquid. All right, section 3, finding the perfect temperature. There is a bit of a Goldilocks principle at play with pyrolysis. Based on testing with low-density polyethylene, or LDPE, if you run the reactor at 200 degrees Celsius, it's just too cold. The plastic melts, sure, but the molecular chains don't break enough, so you end up with a solid wax rather than usable oil. If you push it to 400 degrees, it's way too hot. You end up triggering secondary reactions where the oil vapor breaks down even further into non-condensable gases like methane and hydrogen, which significantly lowers your liquid oil yield. But 350 degrees, that is the absolute sweet spot. It maximizes the liquid oil yield before those secondary gas reactions take over. What's really fascinating is what's happening on a molecular level here. Higher heat literally changes the structure of the resulting fuel. As you increase the temperature toward that 350 to 400 degree range, you cause intense thermal cracking. This forces the abstraction of hydrogen atoms, meaning the molecules rearrange themselves. Carbon-carbon bonds form, and you create complex, energy-dense structures like long carbon chains and cyclic compounds. You aren't just melting plastic anymore. You're chemically re-engineering it into a premium fuel structure. And that brings us back to that prototype. During a 60-minute test run, the engineers operating that carbon steel prototype successfully hit 346 degrees Celsius right at the 40-minute mark. This perfectly aligns with the chemical sweet spot we just talked about. It proves that a localized, miniature reactor can easily reach and maintain the ideal thermal decomposition state without needing some massive billion-dollar industrial infrastructure. Section 4, testing the pyrolysis oil. Let's rapid-fire some physical properties, because the data here is kind of staggering. When researchers analyzed the oil produced from low-density polyethylene, they found its density perfectly matches commercial gasoline. Furthermore, as the process hits that 350 to 400 degree range, the viscosity, the thickness of the fluid, lands right in the exact range of commercial diesel. The flash point, which is the lowest temperature it can ignite, sits safely right between gasoline and diesel. So the takeaway is that this isn't some theoretical, abstract substance in a lab. It is a highly tangible, completely realistic substitute for the fuels we pump into our cars every single day. And get this, look at the octane rating. Octane measures a fuel's ability to resist knocking or spontaneously igniting under pressure in an engine. Remember those complex cyclic compounds and alkyl groups we mentioned forming at high temperatures? Well, they give this oil a fantastic octane rating. Standard commercial fuels sit around 88 to 92. The LDPE pyrolysis oil clocks in between 91.8 and 92.9. It easily matches, and in some cases even exceeds, standard pump fuels. Now, to be completely transparent, it isn't 100% perfect straight out of the condenser. As researchers note, the calorific energy value, basically the sheer amount of raw energy it holds, is slightly lower than a top-tier commercial standard oil. But that's not a deal-breaker at all. By just mixing it with other additives or introducing it to further standard refinery processes, we can easily bridge that energy gap, making it entirely viable for commercial engines. Finally, Section 5, Scrubbing the Toxic Exhaust. I kind of like to think of the tail gas as the final boss of the pyrolysis process. Even without oxygen in the main chamber, the resulting gases contain harmful pollutants. If PVC plastic slips into the mix, it generates hydrogen chloride, which is an acidic gas that corrodes equipment and damages the environment. You also have volatile organic compounds, or VOCs, and carbon monoxide from any incomplete reactions. If we fail to capture these toxic byproducts, the entire environmental mission of recycling this plastic is completely defeated. Thankfully, modern gas treatment systems stack their defense mechanisms brilliantly. It's basically a three-stage shield. Step 1, the exhaust passes through wet scrubbers, where alkaline solutions literally wash the gas, neutralizing dangerous acids like hydrogen chloride. Step 2, the gas flows through activated carbon filters, which trap the remaining volatile organic compounds and eliminate foul odors. And Step 3, thermal oxidizers take over, utilizing high heat to cleanly burn away any lingering carbon monoxide, converting it into harmless carbon dioxide and water vapor. So does it actually work? Absolutely. A mid-sized European pyrolysis plant used this exact integrated approach. By combining wet scrubbers, carbon filters, and catalytic oxidizers, they were able to slash their hydrogen chloride emissions by over 95%. They also reduced VOCs by 90%, bringing all their emissions well below strict regulatory limits. But it's not just about relying on fancy equipment at the end of the line. The best plants employ simple operational best practices. For instance, feedstock sorting. If you meticulously sort out PVC plastics before they ever go into the reactor, you prevent toxic acid gas from forming in the first place. Add in stable temperature optimization, regular maintenance, and continuous digital monitoring, and you've got a clean, sustainable loop. And honestly, the tech is only getting better from here. We're already seeing emerging technologies that'll make gas scrubbing cheaper and way more efficient. Biofiltration uses microorganisms to literally eat and degrade VOCs biologically. Meanwhile, advanced membrane separation will soon allow plants to selectively filter out specific toxic gases at a molecular level with incredible precision and way less energy. Which brings us to a final thought for this explainer. We've seen the science, the prototypes, the fuel quality, and the clean emissions. If localized, mini reactors can safely turn the plastic trash suffocating our planet into a viable, clean-burning fuel. Is waste just a failure of our own imagination? The technology exists today to completely redefine our relationship with garbage and unlock a massive new wave of localized green energy. Think about that the next time you throw away a plastic wrapper. Thank you so much for learning with me today on this explainer. Keep questioning, keep learning, and I'll catch you next time.